Awesome, thank you, and take it away.
Thank you so much. Thank you for inviting me, and thank you all folks for coming to this talk. My name is Adam. I came from Poland. Actually, last week I was in Boston, so it wasn't that far flying to here. And I used to live in Seattle, so it's always fun visiting this city again. So what we are going to do in the next 30-something minutes is we are going to see how we can actually automate the stuff when it comes to monitoring, observability, databases, and everything around. We are going to see that, hey, when it comes to DevOps, we really learned how to do it. We really changed the world over the last decade. We automated so much and we built the right tools, but databases, they are still on the side. They are still not covered with DevOps. Sometimes we call things like DBOps and we think about doing something better, but we are not there quite yet. And in this talk, we are going to see what we can actually do today, what we need to do in the upcoming years, and how we can include databases in our all DevOps principles. So this is the idea. So the agenda for this talk is we are going to first cover what breaks with the databases, right? Our ultimate goal is to build proper observability around the databases. So in order to build this observability, we need to know, okay, what may go wrong, right? We are going to see a couple of examples, how things can break, and why we are not covering them yet, even though we have DevOps, CI/CD pipelines, automated tools, infrastructure as code, and all the other stuff, right? Then we are going to understand what we need to fill those gaps, what we need to build, and we are going to actually build the stuff. And there will also be machine learning in that, so we are going to see how to automate everything and use machine learning to make our lives even easier. So what happened over the last year, last decades, 15 years, whatever you name it? Before that, like in early 2000, the world was so simple, right? We just had monolithical application, one database, maybe a couple of nodes running on IIS, as it was mentioned in previous talk, and that was it, right? Whenever we had a problem with our applications, it was relatively straightforward to figure out where to look for the solution, what's going wrong, right? It was the database, so we had just one database, let's go check it out, or it was the application, right? And we had monolithical application, probably some logging, that could be it, right? But the world has changed, unfortunately. Nowadays, whenever we deploy something, it's like tons of things. We have multiple databases, SQL, NoSQL, vector databases, all the other stuff, right? We have multiple microservices running serverless, regular microservices, Kubernetes, and all the other stuff that we deploy many times a day. And the worst part in this is everything speaks with everything. There is constant traffic on the network. Everything is talking to each other. And when there is a problem, we have no idea what may be going wrong, right? Sure, there may be a fire, and our monitoring solutions may show us, hey, there is burning something over there, but we have no idea whether the fire started over there, whether this is the actual source of the problems, or maybe it's just a coincidence, something manifested in that place, but that's not the source of the issues. So that is the biggest issue, and what can we do about that? Well, we can build monitoring, right? Previous session covered monitoring. I'm not going into that route yet, but I just want to bring to your attention that, hey, if you put a dashboard like that, this is great, but developers hate it. Why? Because, well, it swamps us with data points that are kind of meaningless. We know CPU spiked, and so what? Memory is like we use more memory. So what? What do I do with that? Is this expected? Is this a problem? Should I upscale my machine? Should I reduce the memory usage? Should I just replace everything and start from scratch? What do I do? Those dashboards do not give us a clue what's going on. And unfortunately enough, all those monitoring solutions, name it like Datadog, Dynatrace, whatever else, they quite often go for quantity. Right? They boast we can accumulate 20,000 different metrics just like that, right? But hey, do we need 20,000 different metrics? I understand there is CPU, memory, operating system, database, runtime, network traffic, yada, yada, yada. Do we need all of that? We have no idea what to do with that, and we are just swamped with those. Things get even worse when we actually start discussing how to build alerting on top of that, right? How to configure thresholds, how to tune that, what to do when we have thousands of alerts, right? Is this a problem or not? And generally, it's not straightforward how to deal with all that stuff. And in order to fix that, we need to understand, okay, what is the essence? what breaks when we are talking about databases? It's not about that CPU is spiking up. Okay, CPU may be spiking up because we are getting different traffic, and that might be a bug in our application. But at the same time, it may be that we actually screwed up configuration, network is slow, or maybe some hardware is malfunctioning, right? So we need to understand what can go wrong in order to automate all of that. Our goal now is, let's understand things about databases so we can automate tuning them and fixing them so we don't need to do that manually. And whenever we actually talk about databases and problems around them in general, we can categorize them in like those three different areas. The first area is code changes. Basically, we modified the code of our application and we screwed up, right? We changed the SQL statement, we started getting different data, we modified something, the query is now slower, things break, right? That is relatively easy to figure out. Why? Because we are working on the code, we have unit tests, we have CI/CD, we kinda can pin that down like to, code changes that we are doing, okay? The other thingy that that may go wrong is schema changes. So whenever we add a table, remove a table, change column data type, or whatever else, things may go wrong when we start deploying that to production. Why? Because we need to run schema migrations. Schema migrations are easy when our databases are like 100 rows big, right? Because then it's super easy to just mutate everything. But once we go to live databases that have millions of rows, then schema migrations may take minutes or even hours. And the longest schema migration I ever heard of was taking over a month. So if you click deploy on Friday afternoon and then you realize it's gonna take a little bit over a month, that might be problematic, right? But generally, okay, we know schema migrations can be dangerous. We do not cover that in CI/CD. We'll get to that in a second, but generally those are problematic. But there is yet another area that we typically miss when we are talking about databases, observability, and other stuff. And this last area is query changes. And I'm not talking about that, hey, we changed the SQL text that is being executed, but we changed the way how the query is executed. We dropped an index, we changed the configuration, we modified caches, we upscaled or downscaled the database, we introduced replication or whatever else. The query that was running well when we tested it in our local environment is now terribly slow in production. Maybe it's like 2 months later, maybe it's 6 months later, and we have no idea what's going on. And this is the part that our CI/CD pipelines and, well, typical DevOps practices don't cover, right? Because whenever we have unit tests or whatever about testing our application, we focus on two things: whether we read the correct data and whether we write back the proper records, right? But we do not check whether we used indexes properly. We do not check whether we have the same configuration in production just like we have in developer environment, right? We miss all those pieces, and they can break in production. And that is important. So let's see some examples where things can break. And I guess for most of us, those examples will be, oh yeah, I know that, been there, done that. But let's go through them to actually realize how many of those there are. So the very first thing is like slow queries, obviously. This is one of the examples I had in production. So let's take some decent example of JavaScript code that we have here. So we have this application code that tries to extract a couple of tables and uses many joins, right? What could go wrong in this? Obviously, we have one big select statement that ultimately takes 25 seconds to execute because it extracts something like 300,000 rows. This is what we have, what I had in one of my production systems. So what is going on in here? Because we are joining so many tables, we are effectively increasing the number of rows exponentially, right? So if we have this many rows, like 100 rows in all of those tables, then we will have exponential increase, and then our ORM libraries, they will try to map that into one single object in JavaScript, as you can see in this code, and that's gonna take end-to-end something like 25 seconds. How to solve this issue? Well, the solution in that case was rather straightforward. You just change the code to run 7 or 8 different queries. And when you first look at it, you may say, whoa, 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 8 queries is kinda dangerous, right? That probably should take long. But the thing here is those queries are super small, so all of them finished in less than like 0.01 seconds, something like that, right? But generally, if you think about that for a second, unit tests in both of those cases will be exactly the same. there will be no change in how we test this code, right? And unit tests will be green in both cases, just because we will have something like 2 or 3 rows in our test, because we will just start from scratch and add 2 rows and that's it. And hey, all is green, let's deploy to production. Not that easy when we go to a bigger live database. The other thing we may do is developers always think about, let's make the code readable. There was this famous book, Clean Code. So let's make this code clean. We have a query at the top that is actually duplicating some of the logic. We want to get boarding passes like 3 times. That's just an artificial example. And we want to double hash the ticket number, just for the sake of, showing some example, right? So you can see there is this code duplication in those 3 lines. How about extracting that to a CTE, common table expression? For those of you who are not familiar with that, it's kind of like in-memory temporary table just for the duration of this query, right? So we calculate this double hash of the ticket number here. It's calculated like just once in the code. So if we need to change it to like triple hash, we just change it once instead of 3 times as in this example, right? All is good, we deploy to production and bang. The query at the top runs in 8 seconds when we have something like 8 million rows. The query at the bottom takes 13 seconds to complete, right? So just a tiny code change that leads to better readability of the code and better maintenance nearly doubles the execution time. And obviously developers, they tend to do many changes like this one, right? Again, unit tests won't capture that at all. Your integration tests won't capture that at all. You may yell, hey, we have load tests. We'll get to that in a second, so no worries. But your typical test suite won't cover that. Let's carry on. Changes in schema. Whenever we talk about changes in schema, adding tables, adding columns, dropping columns, changing column type, that's always dangerous. And we probably all know how to deal with that, especially with dropping columns. First, rename it, make sure there is no application touching it, yada, yada. Then, probably 1 fiscal year later, finally drop the column, right? So we know all the year-long reporting is now complete, okay? But the thing is, whenever we, for instance, change the column type, it may be that our application still works properly, meaning that it can read the data and write it back, but now it's crazy slow. Why? Because it serializes the things to string or JSON or whatever else, and your ORMs may go really crazy about doing that. So generally, all the schemas, again, pose the same problem. Whenever we want to deal with testing, we generally test the things and, well, they are green because we just read and write the data back, right? Not to mention that our tests, they typically deal with the final schema. Think about that. We very rarely run tests that are actually running the schema in them. We either go against the old schema, or we just, drop everything, start from scratch, apply all the schemas, bang, and then our testing procedures begin to run, right? So this is yet another problem that we have here. Another thingy is about missing indexes, obviously, right? We run a query is slow, so we need to add an index, right? There are so many different types of indexes. They change over time. PostgreSQL introduces more and more. They are tuned, optimized, yada, yada. But the ultimate thing is, whenever you tell to a junior developer, hey, if your query is slow, there is this one tiny trick. They will love you for that. Just add an index, and we end up with this one. So too many indexes, we have all of them. And the thing about that is, yes, indexes improve reading performance, but at the same time, they also decrease the performance of writing the data, right? And while we optimize one part of the application, we may break something else. So that's yet another case. Moving on. Obviously, there are bugs. Ever heard about Halloween problem? I don't see any hands in here. Okay, so let's quickly cover one funny bug around databases that is fortunately part of the history anymore. So, back in the days, I think it was something like 1970s or 80s, there was one single company that they wanted to basically give salary to all the employees. So they wanted to basically run this super straightforward SQL statement. Hey, employee, if your salary is something below 10,000 or whatever, let's increase it by 10%. Okay, all is good. But then you run into a very fancy bug in your database that it orders the rows based on some value, just like with clustered index, right? So it orders the rows based on what? Salary, you get it. So you scroll through all the rows, you find the row, oh, this one is below 10,000, let's increase it, so the row goes down. Let's carry on. Oh, there is a row. It is still below 10,000. Let's increase it. And bang, everyone was earning at least 10,000 in this case. Fortunately, those bugs are now long gone, meaning all the databases, they know how to protect themselves from Halloween problem, but generally there are so many other bugs in the databases. And if you are interested in those, I highly recommend taking a look at the Jepsen project. Jepsen project is actually suppose they try to analyze all the distributed systems, especially databases like our beloved Mongo, that Mongo claimed obviously cap theorem is no longer a thing, we deal with all of that, but then we learned, okay, when it's high stress, then it just loses the data, so this is how it deals with it, right? Those days are gone, they claim so. But anyway, take a look at Jepsen, how many things can break with databases. Yet another big group of problems is ORMs, right? Whenever you have an ORM, one of the important issues you immediately learn about is N+1 select. So we have table aircrafts that is in relation one-to-many with seats. We want to basically get all the aircrafts, iterate over the aircrafts, and then for each aircraft do something. If we configure our ORM incorrectly, this generates N+1 queries. Why? Because we get one query to get the aircrafts, and then for every single aircraft, we send yet another query to the database, right? This all could be done with just one query that uses join, but you need to configure your ORMs to do that. This is called eager loading. And typically ORMs, they prefer to do lazy loading. Why? Because it's faster, doesn't bloat the memory, and gives you problems like this. Yet another thingy, once again, unit tests will be green in both cases, but your performance will go crazy. Another thingy is joins. Yet another thingy is polymorphism. We have many more examples of how things break. I am not going to go into all of that, but I just want to mention that all the things about databases in our applications, they are hidden from us. They are scattered throughout the code base. Some of them are like in database configuration. Some of them are in the user code. Some of them are in the indexes, in ORMs, in the yada yada. And even if we have infrastructure as code, even if we have unit tests, pipelines, CI/CD, and all the stuff, then we have this issue that we miss all those problems, and we learn about them when we go to production. So tests, do they work? And my point on that is rarely. You really need to test explicitly for those database issues in order to catch them, and most of us don't do that. But hey, you may say, load testing, that is the solution, right? So you can always run load tests against your enormous production-like database, and you get all the issues like that would happen in the production. And this is correct, but there are a couple of problems here. First, building good load tests is generally tricky and expensive. You need to get the production-like data, have the same data distribution, keep it on the site, so it costs. You need to deal with privacy, GDPR, California Protection Act, other stuff, right? Second thingy, load tests are slow to execute. Good load tests take hours to complete, and I mean hours, 12 hours, 24 hours. That depends on what product you are working on, but generally you can easily count that you start load tests, you come back the next day to see the result, right? And the third and foremost is load tests happen at the very end of the pipeline. So we already implemented the code, review it with our teammates, everyone was like, looks good to me, deploy. We merged that, started deploying everywhere, then we run load tests, and this is the moment we learn, oh, something is wrong, and we need to start from scratch, go back to whiteboards, and figure out how to fix that, right? Unless you run load tests on your laptops. But anyone doing that? Yeah, thought so. So generally, load tests are just way too late in the pipeline. And that's the biggest issue with load tests. Yes, they will find a couple of problems, not all of them though, but they are way too late, too expensive, and hard to write and manage to be useful. So what can we do about that? How can we build this monitoring observability and improve the state? The solution to that is database guardrails. We need to build an approach that proactively checks for all the things that we discussed, starts very early in the software development lifecycle, and covers what we typically do with databases. So the very first thing to understand, whenever we want to fix those issues, We need to actually be able to reason about them. We need to see what the problems are. So what we need to do first in order to fix what we are talking about is we need to build proper observability. And there are a couple steps along the way to do that. First step is obviously telemetry. Telemetry meaning that we can extract or emit signals like traces, logs, metrics, and other stuff from our application. Telemetry was something we hated a couple years back. When Microsoft was introducing telemetry with Windows, we were like, hold on, no, not doing that. But nowadays, it's open, standardized, there are good libraries for that, and generally every single application does that. If you don't like that, sorry to say, but hey, this is how the world looks like now. So we have this telemetry that allows us to emit those signals. Then what we need to do is we need to plug in telemetry to all the pieces in our code base, in our ecosystem. That means application, queuing, database, service buses, whatever else, and this builds visibility. Finally, we have the visibility so we can check whatever we need from whichever part of our ecosystem. And then we can build APM, Application Performance Management, meaning that we have nice dashboard telling us it's all green or, hey, there is something wrong. There is red color, we don't like it, right? But this is only the beginning. We then need to build a proper observability around that stuff. And what is actually observability? Whenever we think about monitoring, how we have it typically is monitoring is about errors, metrics, swamping you with 20,000 of signals from whatever in your infrastructure that we don't care about alerts that we don't know how to reason about and then we just close or ignore, or generally all the stuff that is really easy to capture but doesn't give us the most important thingy, which is what to do with that. How do I fix that? Right? Okay, CPU spiking, but what do I do with that? It's Friday night, I want to go home, and I have no idea what to do. And observability needs to give us those answers. Observability needs to connect the dots from all the parts of our SDLC, all the parts of our pipelines, to tell us what's going on in our application. So it's not that your CPU spikes, but it's that you deployed on Wednesday this change, it modified the query, now the query is not using an index anymore, it's Saturday night, you have different traffic distribution, that's why this query is now executed much more often, and that's why your CPU spikes. What do? Fix this index. This is what observability does for us. How do we build that? Well, in order to do that, we need to understand how databases work. So we need to understand a little bit of internals. Whenever we send a SQL statement to a database, it generally goes through a couple of stages. The most important stage of all of them is basically planner. Planner is the part of the SQL or NoSQL or generally any database, decent database engine, which is responsible for figuring out, okay, how do I execute this query? So whenever you run a query, just like we have on this slide here, you can take any select and typically prepend it with explain keyword, and you get something like on the right side of the screen, right? So the plan, how this thingy is going to be executed. Now, what does this plan tell us? When we dissect such a plan, we understand that every single row of a plan is basically an operation. Like, I need to scan table, I need to scan an index, I need to join two tables, and I use this join strategy. For instance, merge join, hash join, whatever else. I need to spill some data to the drive, I need to use buffers, caches, etc., etc. We can reason about what's going on. But the most important part about such an execution plan is what we have in here. This is basically a cost, a number telling us how hard it is to execute this given part of the query, right? And this number is meaningless. It doesn't represent any like quantity, like number of CPU cycles or how much memory we are going to use, nothing like that. But it's just an arbitrary value that we can use to compare plans with each other. So the planner of the database generates many of those plans, many similar plans that differ in like the order of joins, how it stores the data, whether it uses hard drive to store temporary results or not. And then it calculates the cost of each of those plans and picks the cheapest one. That is the idea how it works. And we can always ask our database, hey, tell us, what do you think about this plan? The second thing we need to do, okay, so if we have the query, we can analyze it and reason about it. What can we do next? We need to get the query. So we use the OpenTelemetry library, which is now basically an open standard that lets you extract signals from your applications, like traces, logs, metrics, and other stuff. Basically, OpenTelemetry is a set of SDKs that you use to instrument your applications. If you have like decent modern languages, meaning C#, Java, Python, JavaScript, TypeScript, something like that, then all you basically need to do is add a couple of environment variables and drop the OpenTelemetry binary next to your executable. You do that, and then you have OpenTelemetry in your application, and what you can do with that is you can figure out the traces of your applications. How does it work? Imagine that your workflow, like I'm buying a ticket, consists of like I need to click a button, buy a ticket, and then there is obviously like web server, database, other stuff. So OpenTelemetry can generate something for you that represents the operation that, hey, the user clicked the button, it called this load balancer, then it called this web server, then there was code to this database, queuing system, whatever else, and it can build the thingy that is called a trace. So a trace is basically a history of everything that happened, representing every single step as a span. So span is basically like one single piece of operation that you had to do when working on such a workflow. And this span can include things like human-friendly explanation, timestamps, attributes, etc., etc. And most importantly, it can also capture the SQL statement. So once we have that, we can figure out how to build the modern observability. And the way it looks like is you have your developer environment, so your developer is writing some code, right? They run the application locally, and you have telemetry collector on the side, which plugs into the application and extracts things like, those are the SQL statements that I was running, schema migrations I was running, anything that was happening. You analyze that against the database, and then you push it to some like centralized store. The same you do with CI/CD. But the most important piece comes from your production database. You can also have metadata collector next to production, and now comes the magic. Whenever your developer changes the code, you capture what they do, you project it onto the production database, checking, hey, is it going to run fast enough when I have millions of rows and this configuration of indexes and whatever? And after all, you can tell it's going to work or not. So this is how we can do that early in the pipeline without waiting for load tests and covering everything that you need to do. Query statements, N+1 queries, schema migrations, whatever, talking to the database. So this is how we can do with all this stuff. And now comes the thing. I'm not going to, go much into details of tools that do something like this. I personally, and just to let you know, I am from a company that is called Metis, and we built such a tool. But I just want to show you how it may look like if you build something like this. So for instance, you can have stuff that, hey, this is the endpoint that was executed. This is the query that has been executed behind the scenes. This is the query visualization of whatever was happening, and this is what your database tells you. And ultimately, you can figure out, I have table scan here, and this is the impact, this is the remediation plan, right? This is what you can do when you compose all those data, but it doesn't stop here. If we go into things like monitoring of production database, for instance, we can capture things like transactions, number of rows, tables, schemas, queries, live queries, indexes, whatever else. So we can extract this much of data just to analyze what's going on. And what you can do next is you can automate that stuff. So you go to ChatGPT and you tell ChatGPT in a very direct way, hey, I have this query, so it's running slow. And by the way, this is the JSON explaining everything I have in my database. I have no idea what's in this JSON, right? It's extracted automatically from the system. And you can see, yes, it's long. So you scroll down to the output of ChatGPT, and you can figure out that ChatGPT actually realized that, hey, your query uses those 3 tables, but by the way, you have a couple other tables. How about you create those indexes, right? So ChatGPT can tell you all of that if you just dump this data on it. So this is what you can do now. if you plug in this telemetry and build observability throughout all the pieces in your ecosystem, you can reason about what's going on. You can project that on the production database and figure out, is it going to work well after I deploy it to production? And you can automate the stuff, because nothing stops you from taking this stuff to ChatGPT or building rules about that, or even automating the typical things, just like I showed you in like the product, right? You can see, is there a N+1 problem? Yes, it is. It's super easy to recognize. Then alert. And do not let the user merge the pull request or whatever else. So this is how we can build a proper observability around databases. And when we listen to ChatGPT, this is the example actually I was running with it. You can see I started with a query that was running for like 110 seconds. And after applying the fixes from ChatGPT, went down to 0.3 seconds. Like, that was brainless. I just dumped everything on ChatGPT, copied the query, and off you go, right? And you can automate that. So the summary, to sum up all the things that we discussed, databases may break in many ways. There are bugs in the databases, quirks with ORMs, schema changes, slow queries that we execute, and other stuff. And importantly is, we do not cover that with unit tests. Our testing pyramid does not cover those pieces. Database is not part of DevOps yet. However, if we build proper database guardrails, meaning that we reason about the stuff that we run, queries, configurations, schemas, indexes, and other stuff, we can really easy push all those things to the left and let developers self-service their issues with databases. They can now immediately reason about what's going on in production and how to fix it without waiting for the load test to complete. And the most important part is we can automate all of that. There is really no point in doing manual job, asking DBAs for help, extracting logs manually. We can automate all that stuff. There are already tools out there in the market doing that. Metis is one of them, and we can make our lives easier.